All right. So in this video, I'll be talking through pages 30 and 31 in the notes packet. The first thing I'm going to say is there's a typo here. This 3, we want to change to be a 2. I apologize for that. But it should be a 2 there. I'm not sure what happened when I was typing that. So anyway, these 2 pages are designed to be very similar to your test. This is a good place to put your attention if you were trying to prepare for that. Starting with 1 and 2, you see that we're inputting 0 into the function f, so we must output 4. If we input 3 into the function g, well, we also output 4. If we see f of x is equal to 2, that's saying what do we need to input into for x so that our output f of x is 2. And that would be 3. We have to input 3 to output 2. And solve the equation g of x equals 2. So once again, we see g of x is 2 here. What is the input value we need to set x to be to output 2? Well, that is 0. And now if we try and find the inverse function evaluated at 2, it's important to note that these two are asking the same thing, right? What is the input value where we output 2 in the original function? That's 3. And the reason why is, well, because if this point 3, 2 is on the regular function, then this point 2, 3 has to be on the inverse function. Right, we switch it like that. So if you input 2 to output 3 in the original function, then in the inverse function, you have to input 2 to output 3. So it's backwards. And then g negative 1 of 7 with the same logic is saying, right, we flip the domain and range here. So what we see in g of x is the domain of g negative 1 of x. If we plug in 7, we see that we're going to output 2. All right. And now we have this function down here. We're trying to find the vertical asymptote of it. Well, we know the vertical asymptote will occur when a denominator is 0. So that will happen when x is equal to 6. And now we need to find the inverse of this. So I'm going to start by rewriting it. Y is equal to 3 plus 4 over x minus 6. And I'm going to switch x and y to find our inverse. That means x is equal to 3 plus 4 over y minus 6. Now I need to solve this for y. So I'm going to start by subtracting 3. I'm going to write x minus 3 is equal to 4 over y minus 6. And now I can take the reciprocal of both sides, right? Call this x minus 3 over 1, because we know we can put anything over 1, and then just literally flip both sides. Put the numerator down to the denominator, numerator down to the denominator, and vice versa. And the result is 1 over x minus 3 is equal to y minus 6 over 4. And now I'm going to multiply both sides by 4. And I get 4 is equal to, I get 4 over x minus 3 is equal to y minus 6, meaning that y has to be equal to 4 over x minus 3 plus 6. So f negative 1 of x is 4 over x minus 3 plus 6. All right, now the vertical asymptote of the inverse function, well, that's going to be x equals 3, right? That's what makes this denominator 0. All right, moving on. All right, so now we're looking at page 31, and the first thing I notice is we have an error in the question here. So before you even get started, please change the domain in question 12 to say the range. Apologize for the mistake. And now let's get started. So here we're analyzing a function, but we're doing it visually. So we want to find f of negative 1. It's saying if we input negative 1, what's our output value? We can see that output value is going to be y equals 1. So if you input -1, you're going to output 1, because this point, -1, 1, sits on our function. All right, and then if we see f -1 of -2, the inverse function evaluated at -2, that's like saying for what value does f of x equal -2, right? We know that evaluating the inverse is the same as finding what input for the original function yields that value. So where is f of x equal to -2? That is down here. And so we know we're looking at this point here. And what is the input value required to get an output of -2 in the original function? Well, it is 1. The other way to think about that is we have this point in our original function, 1, -2, which means on our inverse function, we have to have the point -2, 1. And so if we input -2 into the function, we have to output 1. All right, and if we're looking at the range of f -1 of x, this might seem kind of daunting and tricky, but we want to use this kind of property up here, right? For f of x, if we have a certain domain and range, then for f -1 of x, we know that the domain is going to be the range of the original function, and the range is going to be the domain of the other function. So we kind of flip them like that. That means that if we're looking for the range of f -1 of x, that's going to be the same values as if we find the domain of the original function f of x. And so where is the domain of the original function? That is right in this area here. Right, all of the, I can clean this up a little bit better over there. Over here too. So ranging from here over to there, there's the domain of the original functions. The domain of the original function, this is defined anywhere between -2 is less than or equal to x is less than or equal to 1. Meaning that the range of the inverse function has to be -2 is less than or equal to y is less than or equal to 1. Just noting that we change it from x to y because now we're talking about a range, right? We know the values are the same as the domain, but they've been flipped to a range, so we write y. All right, and then looking at question 13, so now we need to sketch the inverse of this on the same graph. For that, I'm going to draw a dotted line up the line y equals x. And so we know we're going to want to flip it over that line. What I recommend doing here is giving yourself some anchor points to work with. So I'll start by just labeling some of the nice points we have on our regular function, right? -1, 1, 1, -2 down here. And what I'm going to do with those functions is, well, we know the inverse function has to have kind of them but backwards. So if -2, 0 is on the original function, well then 0, -2 has to be on the inverse function. And if -1, 1 is on the original function, well then 1, -1 has to be on our inverse function. So I can kind of sketch this in by like starting to connect those. And then another useful tip here is that a function and its inverse will always intersect on the point where they cross the line y equals x. Right? Wherever you cross y equals x, your function and your inverse should cross. Because there, when you flip x and y, well, they're the same thing. So they should be the same point on either function. And then we can finish this by flipping this point, 1, -2, to then become -2, 1. And so the graph is going to carry on to go up there. And so our inverse is going to look like that when we flip it over the line y equals x. So if you are stuck on these, I recommend you use those two tricks. The first one being identify specific points, and then invert the, flip the numbers and graph those new points. Those will give you some anchor points. And then remember that any time that you cross the line y equals x, your inverse in the regular function should flip. All right, and then for these ones down here, we're going to want to analyze a graph using our graphing calculator. So the first thing we're going to want to do, type it into y1. So it's going to be x to the fourth. So x to the fourth minus 5x squared plus 3. So, and let's refresh this. This isn't working super well. X to the fourth minus 5x squared plus 3. Is that the right function? Hold on. No, it should be a squared. I typed a cubed. I said the right thing, typed in the wrong thing. There we go. Now we're on the right track. Okay. See, it's kind of like a W. And when it's asking for the axes intercepts, so that wants both the x and the y-intercept. I'm going to start with the y-intercept because it is easiest. Right, the y-intercept is going to happen when x is 0. So it's going to be g of 0, which means 0 to the fourth minus 5 times 0 squared plus 3. These two terms are going to disappear. So my y-intercept is just 0, 3. And then for my x-intercepts, well, I'm going to need to use my calculator to find those. And go into y equals, and then I want to put 0 there. And then I want to use my intersect function to find the values of all 4 of those x-intercepts. So the first one is going to be negative 2.07. And negative 0.835. And here I'm going to use symmetry. I'm going to say that the other two are the positive versions of that. You can verify that using the calculator if you would like. This is a symmetric function. All right. And then we want to label the turning point. So that's where the graph goes from increasing to decreasing or decreasing to increasing. So to do that, we want to go here, and then we can do the minimums. So we have 1 over here, which we can find like this. You see that it is negative 1.58, comma 3.25. We have minimums at negative 1.58, comma negative 3.25. And again, using symmetry, the other one is going to be 1.58, comma negative 3.25. And then we also have a maximum, which we can do in a second calc. Maximum is going to fall within this range. And it is, so this is one where you can see that we have, it's popping out for x, something times 10 to the negative 6th. That's just 0. There's a little bit of error there. And we know that that's the y-intercept either way. So the maximum is going to be 0, 3. And then the intervals for which it is positive. So that is if x is less than negative 2.07, or if we are between negative 0.835 is less than x is less than 0.835, or if x is greater than 2.07, right? If we are essentially like on the left end of the W before we drop below the axis, in the middle range there, or on the right part of the W. And then where is the function decreasing? That's going to be anywhere left of our minimum, right? Anywhere to the left of negative 1.58. And then again, so then we go from decreasing up to increasing, up until we hit that maximum, and then we're decreasing again until we hit the other minimum. So, or 0 is less than x is less than 1.58. Right, kind of from this maximum to this other minimum, and then after that we're increasing again.